Hello there. So for this exercise we're working with the set of positive real numbers. I'm going to denote it as R with a subscript plus, just to difference from the real, just from R, which is all the real numbers, even including the negative one. But in this case we are working just with positive real numbers. And we're going to equip the set with two operations, the sum operation. The addition, I'm going to denote it with a circle enclosing the sum, because I want to make sure that you difference from the usual multiplication symbol, summation symbol. And the multiplication symbol as well, I'm going to enclose in a circle to difference from the usual multiplication. Okay, so the point is that here in this space the summation is defined in this way. The sum corresponds to the usual multiplication of numbers. So basically I'm going to put here an example to give you an idea. If I pick 2 plus 3 actually means 2 times 3, which is equals to 6. And if I choose 4 plus 5 actually means 4 times 5, that is equals to 20. So that's how is defined the sum on this space. Okay, so it's just a way to define the summation on a space. And if this corresponds to the sum, then the multiplication in this space by a scalar case is any. Here I need to put in context. Here k is a real number. It could be negative, it doesn't matter. The point is that the multiplication by a scalar of a vector, which corresponds just to positive numbers, is defined in this way. So the multiplication corresponds to the power. Okay, so just for give you an example, if I say 2 times 3 in this space, or 2 multiplied by 3 in this space, what I mean is 3 squared, which is equals to 9. Okay, the same, 2 times 2 is equals to 2 squared, which is equals to 4, and so on. Okay, so that's how we define the multiplication and the summation in this space. It could be quite weird, but believe me that there are other different definitions for the summation and multiplication in the other branches of mathematics. So I made this just to illustrate what is happening and to make sure that you understand here the notation, what we are doing. So we need to prove that this space with this operation satisfy the following axioms of a vector space. Okay, so two of them we can already prove just by the definition that we got here. So let me show you. So it is important for you to remember that the first and the sixth axiom of the vector space are related with the closeness of the operation. So the first axiom actually means the close of the sum operation. So if you pick so u and v are elements on the reals plus, that means that they're positive numbers, and if you sum any two numbers in this space, means that you're multiplying these two numbers. Both are positive. That means that the result will be positive as well. Sorry, it's positive, not negative. Yeah, so they are positive. That means that when you multiply two positive numbers, you obtain also a positive number. Therefore, the summation also give you a positive number. Therefore, lies in the same space. So the sum is closed. So you can say that the first axiom is satisfied. Now we need to check what happened with the scalar multiplication. In this case, you need to be careful, because k is any real number. It could be even negative, but that doesn't matter, because u is positive, and a positive number raised to the power, to any power, it doesn't matter if it's negative. K is any real number. This will still be positive. So just to illustrate, I'm going to give you an example. So for example, 4 to any negative value, that's -2 for example, this is equals to 1/16, and this is still a positive number. Okay, so you can see that the negative sign, or choosing negative numbers in the powers, doesn't affect the sign of the whole number. So you again obtain a positive number. That means that the scalar multiplication into space returns you an element of the positive real numbers. Therefore, like in the same space, and the sixth axiom is also satisfied. So we have checked two of the axioms. We have 5 remain. So let's keep moving. So one of the axioms is related with the commutativity of the summation. So I'm going to expand this expression together. So u plus v in this space corresponds to u times v, the usual multiplication, and this v times u. U and v are positive numbers, therefore they are real positive numbers, so they can commute. They commute with the multiplication. That means that this is equals to u times v and u times v. So yeah, the second axiom is also satisfied. The next one is the associativity. So again, I'm going to expand both expressions at the same time. So here we got u plus, and let me expand this expression first. So this equals to v times w, and on the right hand side we got u times v plus w. This is still a real number, so we can operate here again, and we obtain u times v times w, and here the same. U times v times w. So yeah, it holds. This kind of tricky, and that's why I decide to put here on a circle to differentiate with the usual summation. Remember that in this case, k and m are real numbers. They are scalars. They are not the elements on your vector space that corresponds to the positive number. So they are totally different. So these two numbers doesn't operate with this sum here. They operate with the sum on the reals, the usual summation, the sign that we usually use. Okay, so that's why I choose this notation with the circle. So k plus m is just the usual summation over real numbers. So this is again a scalar. So we can consider this just one scalar. So let's see what's going to be this. So remember that the multiplication on this space corresponds to the power. So this becomes u to the power of k plus m. Okay, so that's the left hand side. Now let's see what happened with the right hand side. So the right hand side is k times u plus, here we use the plus on the space because we are operating with positive numbers, and here we got m times u. Okay, so we got this. So let's solve first what is inside of the parentheses, that are the multiplications. So this is just uk plus um, but the summation in this space corresponds to the usual multiplication. So that means uk times um, and this we know that corresponds to some of the exponents, so k plus m, and you can see that both of these expressions are the same. So yes, the 8 axioms is satisfied in this space. Here happened the same. Here this corresponds to scalar numbers, so they obey the usual multiplication, not the multiplication of the space. Okay, so you need to be careful. That's why when you have a kind of different way to multiply on a space, I prefer to do this kind of notation. It helps you to don't confuse with what we are operating on the vector space or in any space. In this case, this is not necessarily a vector space. We need to prove the other axiom, so I'm not sure if it is or is not. Okay, so let's see what is the left hand side of this equality here. So k times, let's expand this expression here. We know that this is going to be u to the power of m, and then this again. So this is going to be u to the power of m to the power k. And we know that power of powers corresponds to the multiplication of the exponents. That means u is equals to km, the usual multiplication here. And if you check what happened on the right hand side, here we got km multiplying in the usual way times u, and this is the multiplication on the space. So these act as a one scalar. So when you multiply this one scalar by u, what you obtain is u to the power of km. And voila, these two elements are the same. So the 9th axiom also holds. And the last axiom that we need to verify is the 10th axiom. It's in general this is trivial, but in this case it is kind of trivial, yes, but in general when you have a different definition of the multiplication or the sum, you need to be careful with what you're operating here. So 1 times u, it's going to be u to the 1 power, and this is again u, so yes, it is also satisfying.